Hello students. So up until last class we looked into differentiation of a vector and also integration of a vector. So it is basically somehow motivated from the integration of scalar function. So we saw that if we have an integral of type, let us say t running from a to b, if we have a vector, let us say f t dt, where the function f t is given, it can be x t I plus y t j plus z t k. Then in that case we basically substitute this this vector f t as this one here in this integral, and we integrate component wise. So for example, if we have an integral of type let us say 1 to 2 f t dt, where our f t is t square I plus 2 t j plus sin t k. So then in that case we just integrate, we substitute this f t here in this integral, and then we integrate component wise with respect to t, and that would give us the integral of this vector function. Now this is called as integration of a vector, but in couple of chapters later we'll come to the topic of vector integration, which is slightly different. So we'll also learn about those things. Now today I'm going to introduce another important topic which is quite relevant from vector calculus point of view. So today's topic is gradient, divergence and curl of a vector function. So by the way, gradient is taken on a scalar function, and divergence and curl will be taken or is taken on a vector function. So it is not like gradient of a vector function, it is always like gradient of a scalar function and divergence and curl of a vector function. Now to give you a formal definition, it goes like this. First of all, what do we mean by how to say partial derivative of a vector function? So in case of scalar functions, we saw that if we have a function of two variables, then in that case we can talk about. So let us say if we have a function of two variables, then in this case in scalar case we can be able to talk about del z del x and del z del y. So similarly, in case of vector function, suppose our vector function r is equals to vector f x y z, then in that case here I can be able to talk about the partial derivative of this vector function. So how do we basically define the partial derivative of a vector function? So let me give you a formal definition. So suppose definition is, suppose r is a vector function, depending on more than one variable, and scalar variable of course, and let r equals to f x y z, that is r be a function of x, y and z. So basically r is a vector function of three scalar variables x, y and z. So you can imagine a vector function of type 3x square z times I plus y square z times j and plus z square x times k. So that can be one possible vector function. So any vector function of these scalar variable r can be of that particular function. Okay. Now then the partial derivative, then the partial derivative, the partial derivative of r with respect to x is given by, how do we define? We define it as del r del x is equals to limit delta x goes to 0 r of, or f r is equals to f. So, f x plus delta x comma y comma z minus f x y z divided by delta x. So, this is how we define the partial derivative of r, which is basically a vector function of 3 scalar variables x, y, z. Similarly, we can define the partial derivative of r with respect to y, then we add a small element delta y, like we usually defined for the scalar functions. So, for the scalar functions also we define the derivative in the similar fashion, and when we define the derivative with respect to z, we write del r del z and then limit delta z goes to 0, and then we add a small increment in the variable z. So, this is how we define the partial derivative of r with respect to x, y and z. If we want to define the if we want to define the successive derivative, so I mean successive partial derivative, that means del square r by del r is del square r by del x square, then we simply write del x of del r del x del square r by del y square is equals to del y of del r del y, where r is a vector, or if we are defining the mixed derivative, so del x del y. So, this will be basically del x of partial derivative of del r del r del y. So, this is how we define the mixed derivatives. All right. Now, that we have introduced the concepts of partial derivative of a vector function, we can actually introduce an operator, and that operator is called as gradient. That operator is called as gradient of a vector function. So, how do we define it? So, let f x y z be a scalar function, be a scalar function, and it is differentiable at each point x, y, z in a certain region of space, then the gradient of f, written as or simply grad f, is defined as gradient of f is equals to del f del x times I del f del y times j and del f del z times k. Some people also write it as del f del x comma del f del y comma del f del z. So, instead of writing I, j and k, we can write it as a triplet, and here this symbol here is called as nabla. So, usually in vector calculus, nabla is nothing but, so nabla is nothing but del x times I, del y times j and del z times k. So, this is our nabla, and some people also use the notation of triplet. So, del x, del y and del del z. So, this is the notation for nabla. So, usually when we say that gradient of f, then we are actually charging this operator. So, this operator is called as nabla, and when you are charging on a gradient function on a scalar function, then it will be called as the gradient of a scalar function, and obviously it is a vector quantity. So, gradient of a scalar function is a vector quantity, and when of course, in this case you must have all the partial derivatives to be existing for that scalar function. And we can also note that gradient of a scalar field defines a vector field. That means gradient of a scalar point function defines a vector field actually. So, if f is a scalar point function, if f is a scalar point function which we defined earlier, then gradient of f is basically a vector point function, or if f defines a scalar field, then gradient of f defines a vector field. All right. Now, let us calculate. So, find example. So, find the gradient of f where f is obviously a scalar function. So, where f x y z is equals to 3 x square y z. So, that is our given function, and we need to find gradient of f here. So, let us do that. Gradient of f is equals to del f del x I del f del y j and del f del z k. So, now if I do del f del x for this function, then it will be 6 x y z, because we are differentiating partially with respect to x only. So, y and z will be treated as constant when we are differentiating with respect to x only, times I, plus when we are differentiating with respect to y, then x and z will be treated as constants. So, this will be 3 x squared z times j, and when we are differentiating with respect to z, then x and y will be treated as constants, and then it will be 3 x square k. So, this is the required gradient of the function f, and that is how we calculate. So, based on this, you can calculate gradient of any scalar function, provided it has partial derivatives that exist. So, we can consider another example. Let us say, so find gradient of f where f x y z is 3, or let us not have 3, I can consider x cube sin y cos z. So, here obviously this is a differentiable function, at least with respect to x, y and z individually. So, then we can write gradient of f is equals to del f del x times I del f del y times j and del f del z times k. So, now when we differentiate f with respect to x only, then it will be 3 x square sin y cos z I, plus when we differentiate with respect to y. So, it will be x cube sin y is cos y cos z j, and when we differentiate with respect to z, then it will be minus of sin z. So, I can have here, instead of plus, I can have minus. So, this will be minus x cube sin y and then sin z k. So, that is how we basically calculate gradient of a scalar function. All right. Now, there are certain results that are I mean, how to say, valid for two functions basically. So, suppose if you have two addition of two functions, then if you charge the gradient on that sum of two functions, what would happen to the sum? So, like we did for the differentiation or limit and continuity for the sum of two functions, or difference of two functions and things like that. So, I would call them as properties. So, properties of of the gradient of a vector function. So, what are the properties? So, statement is let f and g be two functions of scalar variable x, y and z, and gradient of f and gradient of g exists. So, they are defined in a way, then exist actually. Then the first property is gradient of f plus g would be gradient of f plus gradient of g. So, that means gradient of the sum is equals to sum of the gradient. Similarly, if we have a difference here, then gradient of the difference is equals to difference of the gradient. All right. So, let us write a minus sign here. I can try to prove addition and then the subtraction follows in the similar way. So, let us try to show at least one result. So, gradient of f plus g is equals to del x times I del y times j plus del z times k times f plus z. So, this would be del x del f del x times I plus del g del x times I del f del y times j plus del g del y times j plus del f del z times k plus del g del z times k. Now, we gather the f how to say f terms at one place and g terms at one place. So, this will be del f del x times I plus del f del y times j plus del f del z times k, and then plus we will gather the terms for I. So, del g del x times I plus del g del y times j and del z del z times k. So, now this is basically our gradient of f. That is how we defined the gradient of f. So, I can write this as gradient of f plus this one is my gradient of g. So, I can write gradient of g and this is the required result. So, the gradient of the sum is equals to sum of the gradient. Similarly, we can prove the gradient of the difference is equals to the difference of the gradient. So, the proof is not that complicated. Now, we can also have a result or property that gradient or gradient of the product, or we also write as by nebula symbol. So, gradient of the product equals to f times gradient of g plus g times gradient of f. So, it is the similar rule like differentiation of two functions. So, the first function would remain unchanged, differentiation of the second function, and then second function would remain unchanged and differentiation of the first function. So, it follows pretty much the similar or exactly the similar rule like the differentiation of two functions. So, this proof is also very easy, and I am leaving this up to the students, and I am pretty sure you can be able to solve it. The third property is let f and g are be two vector functions such that their gradient of f and gradient of g exist. Then we can write gradient of the quotient. So, the gradient of the quotient would be g square g times gradient of f minus f times gradient of g. So, this is how we define the gradient of the quotient, And of course, the proof is not that complicated to see, because here we have a quotient. So, if you differentiate with respect to x, y or z, then it will always be 1 by g square, and then you are doing the differentiation for the rest of the function. So, it is fairly simple to prove. It might be a little bit lengthy, but of course, you will get to practice a little bit more in this sense, but the proof is very straightforward. So, I am leaving this task up to the students, so they can be able to solve it. I am pretty sure about it. Then we have another small result. So, the fourth property, that the necessary and the sufficient, the necessary and the sufficient condition for a scalar point function to be constant is that gradient of f must be a 0 vector. You always have to pay very close attention that gradient is a vector function, but divergence is a scalar function, which we will define in probably in our next lecture. However, again the curl of a vector function is again a vector. So, divergence is a scalar function, divergence of a vector function is a scalar. However, the gradient of a scalar function and curl of a vector function, they are all vector quantities. So, you have to pay very close attention that whether it is a 0 vector or just 0. All right. So, the necessary condition is that if we have a constant function, then their gradient, then the gradient would be 0. So, it is very easy. So, necessary condition, this implication. So, it is very easy to see if f is constant. So, let f x y z is equals to a constant. So, I call this constant as c. So, obviously, from here we will have del f del x, del f del y and del f del z equals to 0, because the function is constant. So, partial derivative with respect to x, y and z would always be 0, and therefore, from here if I write gradient of f, so gradient of f would be del f del x times I, del f del y times j and del f del z times k, and since all these components these coefficients are 0. So, 0 times I plus 0 times j plus 0 times k, this will be actually a 0 vector. So, the condition is necessary and that has been established. All right. Now, let us go the reverse way. So, the reverse way, suppose gradient of f is equals to a 0 vector. So, then what would happen? What would happen is we can write it as del f del x times I plus del f del y times j and del f del z times k is equals to 0 vector. So, 0 vector can be written as 0 times I plus 0 times j plus 0 times k. So, now this is sort of like an identity. So, the coefficients must be equal. So, that means the coefficient of I must be equal to coefficient of I on the right hand side, coefficient of j on the left hand side must be equal to coefficient of j on the right hand side, and similarly for the coefficient of k. So, from here I can write del f del x equals to 0, del f del y equals to 0 and del f del z equals to 0. So, if I integrate on both sides of these equations, so if I integrate, then f will be a function of y z only. So, I can write g y z. If I integrate the second equation, then f x y z equals to f will be only a function of h z x, unless the partial derivative cannot be 0. So, unless the function f is a function of h and z x only, the partial derivative cannot be 0, and we cannot write constant because we do not know whether the function f is a constant or not. So, even if the function is a function f is a function of z and x only, its partial derivative can still be 0 without the function f being a constant. So, once you integrate, you should not write constant, you should always write the function of z and x, all right. And when we integrate f, then g h, let us say I have k, then integrating the third equation will give me f as a function of k x y. Now, here we have a problem. One function cannot be equals to 3 different functions unless the function itself is constant, because the function cannot be just a function of y and z, it cannot be function of z and x, and it cannot be function of x and y. So, the only possibility for this function f to be existing is that f x y z has to be a constant. So, that means a constant function. So, that means it must be equals to c. So, unless this function f is constant, these 3 possibilities cannot happen. So, if f is equals to how to say g y, if f is a function of g y, is a function of y z, z x and x y. So, from first equation, from the first solution, we can see that f is independent of x. From second equation, we see that f is independent of y. From third equation, we see that f is independent of z. So, this one, and that means that f is independent of x, y and z, and since f is a function of 3 variable. So, the only possibility f has is to be a constant. So, it cannot be any other function. So, that means if the gradient of f is 0, then the function has to be constant, and if the function is constant, then obviously the gradient of the function is 0. So, this is what we needed to prove, and these are some simpler results which we can definitely practice, and we will practice some more examples on gradient of a function, and we will also introduce the concept of divergence of a vector function in our next class. So, I thank you for your attention, and I'll see you in the next class.